We'll wait for a few more minutes for people to join and then get started. Hope you can see my screen and hear me clearly. If not, please post a message on chat. A minute more and we can get started. Can you hear me now? Great. Okay, let's get started. So, welcome to the week 8 live session of the CS100 course. I'm Prashanti. I'm a PhD student at IISc Bangalore and I handle the live sessions at this timing. So, in case people are attending this for the first time, I hope not, but in case, there are 3 of these sessions that happen every week, and you would find the details and timings on the course announcements page on the NPTEL site. And this session is intended to help you with your assignments, so they would have a heavy focus on problem solving. So we will be taking problems that are very similar to your assignment questions, but they would not be the same as your assignment questions. I will also pause 2-3 times during this 1 hour session so that you can ask doubts based on this week's course content. So if you have any questions or any doubts or anything that needs clarification, please feel free to post it on chat. And I prefer the sessions to be as interactive as possible. So I will read out a question, wait for a few seconds or a minute, even if it's a problem solving question, so that you can try and think about it and post whatever you think is the answer on chat. After that, I'll discuss the solution, and then I'll again pause for a little bit so that you can ask if you have any further doubts, right? And audio is typically muted, so chat will be the medium for questions. You will get access to the slides and the recording post the session. So hope this is clear. So as you've seen in your week 8 lectures, the topics that were covered were some continuing with some classical problems on synchronization, which was the dining philosopher's problem, and then the majority of the focus was on deadlocks. So right from what is a deadlock to what are the conditions that are necessary for a deadlock to happen, how do you handle a deadlock, right from how do you prevent it, avoid it, to how do you detect it, and then once you detect it, how do you recover from it, right? So this is what we focused on in the lectures, and today's questions and content will also be focused on this. And for people who are preparing for GATE, deadlocks do have questions in the GATE syllabus too. So I've added maybe 1 or 2 questions from that perspective as well, so that it's helpful for your GATE prep. So yeah, let's get started. So the first question says this: if P0, P1, P2, P3, P4 are a set of waiting processes, under which of the following circumstances a deadlock would arise, considering that mutual exclusion, hold and wait, no preemption conditions hold? So option A, P0 is waiting for resource held by P2, P2 is waiting for resource held by P3, P3 waiting for something held by P1. Option B is P0 waiting for P1, P1 waiting for P2, P2 waiting for P3. Option C is P0 waiting for P2, P2 waiting for P4, and P4 waiting for P0. And you have another option in a similar manner. So I'll give you 1 minute to think about this. Under which of the following conditions would a deadlock arise, considering that the other 3 things hold? Any answers? Think about this. Okay, we have one answer that says C. P0 is waiting for a resource held by P2, P2 is waiting for something held by P4, and P4 is waiting for a resource held by P0. Interesting. Anyone else? Anyone who agrees with C? Anyone who thinks something else is the answer? Okay, You see a bunch of people saying B. P0 is waiting for P1, P1 waiting for P2, P2 waiting for P3. Interesting. Okay, let's take a look at the answer. So it is actually C, which was P0 waiting for a resource held by P2, P2 waiting for a resource held by P4, and P4 waiting for something held by P0. So why is this the case, right? So let's take a quick look at the recap from your lectures on when a deadlock arises, right? So there are 4 conditions that all of which need to be true for a deadlock to happen, and 3 of them which the question said were already guaranteed were mutual exclusion, hold and wait, no preemption. So since we've already gone through synchronization in the previous week, I won't spend a lot of time on mutual exclusion. You guys know what it is. Hold and wait meaning that a process holds at least one resource but is waiting to acquire additional things. So this is one condition where that is needed for a deadlock. Another one is no preemption, which again is quite self-explanatory, right? The resource can be released only voluntarily, meaning it can't be preempted from a resource that is holding it. And now these 3 are guaranteed as said in the question. Now the 4th condition that is needed is circular wait. So what is circular wait? If there exists a set of processes P0 to Pn of those many processes such that one process is waiting for a resource held by the other one, and so on. P1 is waiting for something that is held by P2 and so on, and the n-1th process is waiting for something that is held by Pn, and then the nth one is waiting for something that is held by P0. So basically think of this as a kind of, if you think of these processes as nodes and the edges as indicating that either a process is waiting for a particular resource or it has been assigned a particular resource. Basically, if you think of this as a resource allocation graph, then the circular wait means that there is a cycle in that graph. Now if you look at these processes, maybe a pen would be useful here. Yeah, so here we have 5 processes, P0, P1, P2, P3, P4. Now what is said is P0 is waiting for some resource that is held by P2. Let's simply indicate this with a dependency, right? So the way I am doing this, I am not drawing a full resource allocation graph. You can think of this as maybe a wait for graph, right? And then P2 is waiting for something that is held by P4, and then P4 is waiting for something that is held by P0, and this forms a circular wait condition. So this is when a deadlock will arise, because this cannot be broken. All of these will keep waiting because of this circular condition. Whereas I see that many of you picked B, in which case you have P0 is waiting for something that's held by P1, P1 is waiting for something held by P2, P2 is waiting for something held by P3. But now, because there is no circular connection back here, let's say P3 actually finishes executing and releases whatever it was holding, right? Now P2 can finish executing, then P1 can finish executing, and then P0 can also finish executing. So there won't be a deadlock. So the important thing here to understand is this circular wait condition. Basically, if one process is waiting for something and the next, and this chain continues till the final thing in that chain is waiting for something that the beginning of the chain has. So that's when you call it a circular wait. And it might not, although the definition says that you have these many processes and all of them are involved in this wait condition, right? It need not be the case. As you see in this question, even though you have 5 processes, even if 3 of them are involved in the circular wait, it is enough to create a deadlock, right? So hope this explanation is clear. I'll wait for 30 seconds to see if you have any doubts. Okay, if this is clear, we can move on to the next question. Okay, consider the following resource allocation graph. So again, just as a recap, these are your processes P1, P2, P3, P4, P5, and these are R1, R2, R3 are your resources, right? And the arrows in two direction either indicate that a particular process is waiting for a resource or that it has been assigned a resource. And there are multiple instances of each resource as indicated by these dots that you see in each resource box. Now the question asks you to determine whether there is a deadlock, and you have 4 options: no deadlock, maybe a deadlock, is a deadlock, can't be determined. Any answers? I see that we've already gotten one which says there is a deadlock, one which says there is no deadlock. Nice. So I think deadlocks is typically the chapter where there are lots of possible answers, because yeah, you need to work this out carefully. So I'll wait a little more time so that others can also think about this question. Okay, there is no deadlock. Anyone else? Okay. Okay, most people seem to think that there is no deadlock. Great. Let's take a look at the answer. So before that, I will just quickly walk through this resource allocation graph. Again, you have vertices and edges. I think we went over this, processes and resources. So there are 2 kinds of edges because it's a directed graph. So there is a request edge, which is a directed edge from a process to a resource. And there is an assignment edge, which is a directed edge from the resource to the process. And the basic idea is that if there are no cycles, it implies that there cannot be a deadlock. If the graph contains a cycle, if there is only one instance per resource type, then a deadlock definitely exists. If there are several instances per resource type, then there is a possibility of a deadlock. So with this, the answer is there might be a deadlock. So here, so interestingly enough, I think no one got the answer right. So I think the answers I got were C and A, but that's okay. So pay attention to the answer now. So there is a cycle, there is a directed cycle that's present here, right, as seen from the highlighted arrows. So I am just tracing it with my cursor. So the cycle looks like this, right? But why the answer was not C is because there are multiple instances of these resources. Each resource has 2 instances, right? So here what actually causes the deadlock, or what might cause the deadlock, is P1 is waiting for a resource that is held by P3, and P3 is waiting for a resource that is held by P5, and P5 is waiting for a resource that is held by P1, right? And if there was just one instance of all these resources, the answer would have been C, there is a deadlock. But because there are multiple instances, so for example here, R2 has two instances, R3 has two instances, and currently one instance of R2 and one instance of R3 are assigned to P2, right? And looks like that's all P2 needs, because it does not have an arrow pointing from P to the R. Basically, it does not have any other request edge. So it could well be the case that P2 finishes execution using these two resources and frees up this one instance of R2 and one instance of R3. Now in that case, P3 will no longer need to wait for this, because although one instance of R3 is assigned to P1, there is another instance that P2 has just freed up, right, which P3 can use, and so the deadlock would be broken. So it's not possible to say for certain here whether there is a deadlock, because there are these multiple instances, but there could be a deadlock, which makes the answer B. And that's the main thing that you have to keep in mind. Once you find a cycle, if there is just one instance, then the deadlock definitely exists, and if there are multiple instances, then there is the possibility of a deadlock. Is this clear? Okay, there's a question. Let me see that. Why B with the current resource allocation process can be terminated? I didn't really get the question. With the current resource allocation, processes can be terminated. You mean that there won't be a deadlock under the current resource allocation? Okay, we have been given request edges and assignment edges, not claim edges. I am still trying to understand this. Okay, I see. I still think B is the right answer. If we know what is allocated and process can finish, should be able to say that right. So that's a little tricky to explain. Let me think about this for a bit, and then I think I get your question now. We know what is allocated, and you're saying that P2 can actually finish with this, so there might not be a deadlock, which is true, but yeah, let me think about this and get back. So basically, the moment you find this sort of multiple instances of a resource, right, it gets tricky to say, because yeah, you're not sure when you can conclusively say that there is a deadlock or there isn't a deadlock. So that's why usually the even when you find a cycle, the answer is there might be a deadlock. It's not conclusive that there is a deadlock. Okay, deadlock detection works based on the current. Yeah. So if you were looking at whether there is a deadlock right now, there definitely isn't a deadlock. But the question is whether there could be a deadlock because of this kind of a thing. And the answer is yes, because you have this cycle, right? Because you have this cycle of directed edges, the answer is that it could result in a in a deadlock. And one of the ways that I could think of interpreting that is, right now we are looking at P2 being assigned these two resources, but maybe there is something else that P2 also depends on and might not release these two resources, and therefore this itself is enough to cause a deadlock, right? That's why with multiple instances of a resource, it's not very straightforward, and this what you see is might not be the complete picture. That's why we stick with there might be a deadlock, and not we don't conclusively say that there is a deadlock or there is no deadlock once we find a cycle. But I get your point. I'll think about that a little bit, and if I come up with an answer that goes beyond what I've currently said, I'll put it into the slides and upload it by end of today. Any other questions on this? Okay, let's move to the next question. So it's pretty similar to the previous one. Again, you're given a resource allocation graph, and the question asks whether there is a deadlock or not. So it's simply about seeing if you can find a cycle in this. Any answers to this? I'll wait for another 30 seconds. Does not exist. Great. Anyone else? Okay, deadlock does not exist. Okay. Anyone else? Okay, let's look at the answer. It is does not exist. So for people who thought they saw cycles, this basically it should be a directed cycle, right? So even if one of the edges is reverse in direction, then it does not form a cycle. And once it does not do that, the circular weight condition is violated. So here are two examples where you think it is a cycle, but because this arrow is reversed, it does not form a cycle. So we can conclusively say that there are no deadlocks. Since we're almost halfway through the session, I also wanted to ask, in case anyone has doubts on the week 8 lecture content, please post your questions on chat. I will ask once more towards the end of the session, but feel free to post it. I will either take them up right away or towards the end of the session. I'll pause 30 seconds and then move on to the next question. Okay, let's move to the next one. Select the incorrect statement. If system is in a safe state, there cannot be any deadlocks. If system is in an unsafe state, it implies that there exists at least one deadlock. If a system is in an unsafe state, there may or may not be deadlocks. None of the above. Any answers? Okay, B. Anyone else? Anyone else? Any other answers apart from B? Okay, let's look at the answer. Okay. Okay, the answer is actually C. Apologies for not highlighting it. Yeah, and a quick recap on this. So, think of this in terms of a state diagram, right? So, there are certain states that you can think of as safe and certain states that you can think of as unsafe, right? And there are transitions. Okay, one second, let me read that again. Okay, select the incorrect statement. So, this is correct. System is in a safe state. Great, you're right. B is the right answer. Uh, that's correct. Thanks for pointing that out. And just as a recap for safe and unsafe states, so if a system is said to be in a safe state, it basically means that there are no deadlocks, as this diagram indicates, right? But when we talk about a system being in an unsafe state, it does not automatically mean that there is a deadlock. There is just a possibility of a deadlock. And why it helps in having this distinction of safe versus unsafe is it helps predict when you're going to go to a deadlock state. So once you go to this unsafe state, it's easier to maybe detect and therefore prevent, right? You can easily prevent deadlocks because now you know that from this unsafe state you could possibly end up in a deadlocked situation. So the good thing to do is to make sure that the system always stays in the safe state. So coming back to which is the incorrect statement, C is correct. If it's in the unsafe state, there may or may not be deadlocks. If it is in a safe state, there cannot be any deadlocks. So the answer is B, which is incorrect, because even though it is in an unsafe state, there may not be a deadlock. So this statement that there is at least one deadlock if it's in an unsafe state is wrong. Is this clear? I'll wait for 30 seconds here. Great. If no questions, moving on. Uh, PABC is a set of processes which follow the sequence of A equal to 23, B equal to 12, C equal to 75. All three require the same resource to execute. To ensure a safe state, which of the following is applicable? PC has to wait until PB terminates and PB has to wait until PA terminates. PA has to wait until PB terminates and PB has to wait until PC terminates. PB has to wait till PA terminates and PA has to wait till PC terminates. PC has to wait until PA terminates and PA has to wait until PB terminates. So you can think of these as arrival times, right? This A equal to B equal to C equal to. Which of these do you think is necessary to ensure a safe state? I see one answer saying D. Great. Anyone else? Anyone who thinks a different option is the right answer? Okay, let's look at the answer. It is D. So let's start with this arrival time, right? So let's say B starts executing and it has this resource, and next when A arrives, has to it has to the order of execution will be this way. It would be B, A, and then C. So B will terminate first, and then A. Until then, A and C have to wait, and then once it releases this shared resource, then A would execute and then C would execute. I'm not really sure if this is arrival time rereading the question. I'll again think about this and get back on whether this is arrival time or the sequence is decided based on something else, right? But this is sort of the logic. There's one shared resource, and which means that you have to have a certain sequence of execution, right? And in this case, it is decided by this sequence of numbers that is given. So based on that, A will have to wait till B terminates, and then C will have to wait till A terminates, and that's the sequence that you need for a safe state to be ensured. Right, I know. So these questions are actually picked up from a previous iteration of the same course. So as in maybe 2020 or 2021 iteration of the NPTEL course. So they are actually assignment questions. So I don't set most of these questions. They are given based on previous iterations of the course. So I am not very sure what this means because the question did not have that information. But I'll just try and think about what this could mean and why that number is relevant. Any other doubts on this? You can even think of it as the burst time, right? And maybe the scheduling algorithm is SJF. In that case, it would make sense why B is starting. Why B is picked up first, and then A and C would have to wait. So I'm kind of trying to fit what best fits this situation here. So they probably mean burst times, and then okay, FCFS also gives but in case of FCFS, it is kind of, there are no three processes that are waiting to it depends on the burst time. Sure, FCFS also would give the same thing. Right, this is not very clear. Anyway, just take away from this question that if you have a single shared resource, you need this kind of a particular sequence of execution. That's pretty much it. So based on a scheduling policy and further details like arrival time and burst time, you can come up with the relevant sequence that is needed. Let's move on. Banker's algorithm is used in deadlock prevention, deadlock avoidance with resources allowing single instance, deadlock avoidance with resources allowing multiple instances, recovering from deadlock. So I think this is a fairly straightforward one if you remember Banker's algorithm. Okay, C. Anyone else? Okay, let's look at the answer. It is C, deadlock avoidance with resources. Okay, I see D, recovering from deadlock. It is C, avoidance with resources allowing for multiple instances, right? So, yeah, I'm not going into the details of the banker's algorithm because that will take too much time. But it's broadly it does deal with multiple instances of a resource type, and it just has an assumption or a caveat that every process must a priori claim the maximum use, and other things that when other assumptions or other things for this algorithm, other conditions are when it requests a resource, the process may have to wait, and once it gets all its resources, it must return them in a finite amount of time. So the term banker's algorithm comes from this analogy where you have a line of credit and you borrow money in chunks that don't exceed your maximum line of credit, and once it reaches that maximum you have to pay it back in a finite amount of time, right? It's very similar to that, and hence the name banker's algorithm. And therefore and it is used in deadlock avoidance, right? So C is the right one. I think this is straightforward. In the interest of time, I'll keep moving. Which of the following can be used to recover from deadlocks? Abort all deadlock processes, abort one process at a time till the cycle is eliminated. Ostrich algorithm, A or B? Okay, A or B? Anyone else? Anyone? Okay, let's look at the answer. It is A or B. So a simple thing that you can do is abort all deadlock processes, but this might be too expensive to do, or it might mean a lot of rework to be done, right, for all these processes. So in that case you might choose to do option B, where you start with one process at a time and keep aborting one and hoping that the cycle and therefore the deadlock goes away, right? So both are valid approaches to take, and you might decide between one of them depending on what the system goals are. Ostrich algorithm is not used in deadlock recovery as such. It Ostrich algorithm just refers to the fact refers to a scenario where you pretend that there is no deadlock, right? That's what ostriches typically do, bury their head in sand, and it's used as an idiom, right, where you pretend that the problem doesn't exist and hope that the problem goes away. So that's what ostrich algorithm refers to, and that's not the right answer here. So it could be A or B. Both of them are valid recovery mechanisms. Okay, I will move to the next question if there are no doubts on this. Okay, moving on. Consider a set of 5 processes P0 to P4 and a set of 7 resources R0 to R6. The allocation matrix has a size of 5 cross 7. If the allocation matrix of 3 comma 2 equal to 6, it implies that process P3 has been allocated 6 instances of resource R2, P2 has been allocated 6 instances of resource R3, P3 is requesting 6 instances of resource R2, P2 is requesting 6 instances of R3. P3 has been allocated 6 instances of resource R2. Okay. Any other answers? Any other answers? So it is A. P3 has been allocated 6 instances of resource R2. A quick recap from, so this is from the banker's algorithm, right? So this is the allocation matrix. So allocation of ij equal to k is used to refer to the fact that process pi is currently allocated k instances of resource rj. So the row index corresponds to the process and the column index corresponds to the resource. So in this case 3 corresponds to P3 and 2 corresponds to R2 and the value 6 corresponds to the number of instances that have been allocated. So the option A is the correct answer here. Any doubts on this? If not, we'll move to the next question. Deadlock detection algorithm is invoked depending on how often the deadlock occurs to decide how many processes are needed to be aborted arbitrarily at any point in time, both A and B. Anyone? Okay, depending on how often the deadlock occurs. So this is again a sort of mixed framing, right? So two of the options talk about when a deadlock detection algorithm is invoked, whereas one of them talks about sort of why it is invoked. So the answer given is actually D, both A and B. So this is sort of not exactly the purpose of why it's invoked, but it is a consequence of invoking the detection, right? Once you invoke the detection and then find the deadlock, you also decide how many processes and which processes need to be aborted. So this is not sort of the sole purpose of the deadlock detection algorithm. So I don't disagree. I actually understand why many of you or all of you actually have chosen the option A. The option given in the answer key is D, which is both A and B. But I would say that A is fine as well here, because deadlock detection algorithm is primarily invoked to detect a deadlock, and then a consequence of that is deciding how many and which processes need to be aborted. So A is a suitable answer according to me here. Okay, I think we have another question, so I will write. So this is probably based on what the question was framed, but the framing was not very great, right? So you decide how often to invoke the deadlock detection algorithm based on all of these factors. But yeah, that's fine. I think A can be taken as a suitable correct answer here. Okay, next one. How should we choose the order of process termination to recover from deadlock? How many processes are needed to be terminated? Priorities of the processes to be terminated? How much longer time to completion is needed for the processes? All of the above. So based on which of these factors would you choose the order of the process termination? Whether it is how many processes need to be terminated, or whether it's based on the priorities or based on the completion time. Okay, all of the above. Yes, the answer is all of the above. And yeah, as a quick recap, and there is no one right answer, right? You can have an abortion strategy based on any of these or multiple of these, and each of those comes with their own advantages and disadvantages, just as we saw different scheduling algorithms, all of which optimize for a particular metric. Similarly, you can have different strategies to abort processes to recover from a deadlock. So based on priorities, based on how many processes you need to terminate, or based on how much time to completion, all of these are valid. So that's why the answer is all of the above. So I think this was the last question I had. We are about the end of the session. So I will get back on this question. I am also not very sure if the given answer B is the right one, because as pointed out, this can be resolved. This would not lead to a deadlock, right? So I'll get back on this. I'll update it and then upload the slides. But hope everything else is clear. And if you have any other doubts on this week's course content, please ask. And I think I have one other question that I've put in here, that is from a previous GATE question. So try solving this on your own and ask me if you have a doubt. The answer is also given in the slide. But this was probably a little outside whatever is covered in the lectures. So I won't discuss this here, but hope this is also useful to people who are preparing for GATE. So any other questions? Okay. How important are monitors? Um, I think if you understand the high level idea, it should be fine. But again, I don't know the perspective from which you're asking the question. Is it about exams in from an NPTEL perspective or from GATE? Exactly, I don't know. So from an NPTEL exam perspective, I have no idea how important it is considered to be. I would suggest go through it and understand it well. From GATE, I think. Not, I don't remember seeing questions on monitors, so I would say not so important, but do your own research on that. Okay, if great, thank you. And if there are no other questions, I'll see you guys next week. Thank you so much for showing up and making this an interactive session. See you next week. Thank you.